We're going to be looking at the concept of a pivot position of a matrix. We say that a pivot position in a matrix A is the position of a leading entry in the reduced row echelon form of a matrix of matrix A. So sort of your first step in identifying a pivot position is to get that matrix in its reducer echelon form. And we'll remind you that that form is unique. So once the matrix is in that form, you can identify, precisely where those pivot positions are. And we say that those particular positions in the matrix are pivot positions of that original matrix A, and really of any of the matrices that we saw along the way to getting it into its reducer echelon form. So, whether your matrix is in reducer echelon form or not, once you get it into that form, you can identify the pivot positions and then sort of look back to your original matrix and see them. Going into a few examples. Yeah, so pivot positions correspond to the locations of leading ones after row reduction. And so this matrix itself is not in reducer echelon form, but it's close. If we just do one step here, so we do row 1 minus 2 row 2, then we can get it into its reducer echelon form of 1, 0, 0, 1. And then we can identify our pivot positions. So our pivot positions are going to be, again, these positions of the leading ones. So in this example, the pivot positions occur, well, here's a leading one and here's a leading one. So actually the pivot positions, we look back at that original matrix, are where those two ones were. Going to this example, this matrix is in reducer echelon form, and so we can just sort of identify those pivot positions as being here and here. Notice that we do not have a pivot position in every row or every column, but we do only have one pivot position in each row and in each column, and that's going to be important and something that I want you to think about, that when we get a matrix into reducer echelon form, we will only have a leading one we will only have one leading one, of course, in each row because it's the leading one. So we sort of stop looking at that row once we get to it. But also in each column, because when we are reducing our matrix to reducer echelon form, we make sure to get zeros above and below each leading one. So each column is only going to have, one non-zero. Each column with a leading one, I should say, is only going to have one non-zero entry in it, and it's going to be that one. So something to kind of keep thinking about. Let's look at one more example here. Here again, we have a matrix in reducer echelon form, and so we can identify those pivot positions by the locations of those leading ones. And again, you can see each of those leading ones is the only leading one, of course, in its row, but also, the zeros above and below it tell us that we can only have one leading one in each column as well. So some fundamental questions to consider, and these are going to be related back to pivot positions, and we'll come back to this in a later video, but just something to think about, and then we'll have you go off and practice a little bit, and then come back to the next video. When we encounter a linear system, and actually these questions go beyond linear algebra and linear systems. These are common questions we ask in a lot of math classes and a lot of scenarios. Those are questions of existence. So is there a solution to our system? Some terminology here. If a system has a solution, we say that that system is consistent, and if not, we say it is inconsistent. So existence, and then the second question is related to uniqueness. If the linear system is consistent, is the solution unique, or are there infinitely many solutions? So, going back to earlier in the chapter, we looked at the different possibilities for solution spaces. We could either have one solution, no solutions, or infinitely many solutions. So in terms of a system being consistent, it's possible that we have a consistent system, so we have a solution, but it is not unique, that there's infinitely many. It's also possible that a system is inconsistent, that there's no solutions, or we might have a unique solution, just one. So we're going to look at how pivot positions can be used to answer these questions.